Hey, what's up guys? It's your chemistry tutor here, Caden Law, and today we're going to be talking about electrolysis, specifically over potential. Well, I'm going to assume you guys know what electrolysis is. It's when you power a non-spontaneous process using voltage. So you know what I assume that you know what an electronic cell does and what it is. So I'm not gonna, go too much into electrolysis, but I am gonna talk about overpotential today. And so what is overpotential? Well, in simple terms, basically is when you have to apply a greater quantity of voltage to drive the non-spontaneous process. And I'll explain this later, but first, let's look at an example. Let's say you have NaCl aqueous, right? And you perform electrolysis on it. Well, what is NaCl aqueous? Well, it's made of ions, Na plus aqueous and Cl minus aqueous, right? So let's look at Na plus first. So when you look at this, you might, immediately think that, Na plus is going to be the one that's going to be reduced, right? Because, that's the cation. The cation gets reduced to the solid form. But you have to also consider that there's water inside because it's aqueous. So in this case, water has a much higher reduction potential than sodium does. And because of that, water is actually the one that's reduced. So it's that. Actually, give me a second here. You also have to consider that water is at a pH of 7. So that means this is not actually the standard reduction potential here. It's actually you apply the Nernst equation first and you get the non-standard reduction potential. Because remember, standard reduction potential means that the molarity is 1 molar. But here, OH minus is not going to be at 1 molar for water, right? That'll be super basic. That's not water. Water is neutral. So actually, the standard reduction potential for water would be something like, I think, negative 1.23 voltage, if I remember correctly. I'm not too sure about that, but I think that is what it is. But yeah. Okay, so let's move on to Cl minus. So this is where it gets interesting. So Cl minus, the oxidation potential is negative 1.36, and here we're using oxidation potential instead of reduction potential. So in this case, the higher oxidation potential is the one that has a better tendency to be oxidized, and that's opposite of reduction potential. So you have 2 Cl minus gives Cl2 gas and 2 electrons, and the oxidation potential for that is negative 1.36 volts. Again, you have to consider water here. Right? So the oxidation potential of that is negative 0.82 volts, again considering that the pH is at 7.00. So you might look at this and you might think, well, then that means water is going to be oxidized because it has a higher oxidation potential than Cl minus. And that's where you'd be wrong. And that's where overpotential comes in, because water actually has the oxidation of water actually has a very high overpotential, and that means the actual amounts of voltage necessary to oxidize it is much greater than negative 0.82. Sorry, that looks like a 6, but it's a 0. So actually, what gets oxidized here is Cl minus. That's what gets oxidized. So you might ask, like, how do I predict this? This is so random. And the answer is you can't really predict it. And that's the thing. And that might make you a little, confused and like ask me, why am I teaching you this if you can't predict it? Well, that is a good question. Why am I teaching you this if I can't predict it? But it's important. But yeah, basically you can't predict it. But what I can tell you is that anything that produces oxygen will have a much higher, will have a very high overpotential compared to something like chlorine. So yeah, so the balanced equation for this entire electrolysis reaction would be, you would have water and you would have Cl minus. So you would have 2H2O. Actually, let me type this. So you would have 2H2O plus 2Cl minus gives you H2 plus Cl2 plus OH minus. And that would be your overall electrolysis reaction equation. Thank you guys so much for watching, and I'll see you next time.